So thanks everybody for coming today. I am not the technical committee. I chair the marketing committee. But on behalf of these great guys and all of the members of this alliance who are driving the technical committee and all of the features, today I'm going to give you a little bit of a deep dive in a number of these different areas, some of which were brought up by Donna in the keynote earlier on this morning. So interesting to note that our terminology is TS, which means technical spec, and then TR means technical recommendation. So one is a completely defined specification, protocol transfers, and watchdog timers, and all that kind of stuff. The technical recommendation is more of a guideline how to achieve something, so that we're not all trying to reinvent the wheel. At least we've got a guideline how this is probably best done, like a best practice. So first one is the relay function. So LoRaWAN has a spectacular link budget, and it has awesome coexistence and noise immunity, but eventually the laws of physics catch up. So in order to extend that link budget just a little bit further, maybe into a basement where there might be a cluster of meters, or maybe deep down in a manhole cover, or some other awkward to reach location, a relay could be deployed. That relay is also running on batteries, and I'll come to that in just a second. But that relay then enables that extra jump of range to get a maximum of 16, so 1, 6, a maximum of 16 devices to be able to use that relay to then piggyback the data back into the network. So it's not a true mesh because there is only one relay. You can't put another relay behind the first relay and so on and so on. It's just a one-hop relay just to get down into a manhole, into a basement of a building. As I said, it runs on batteries, and so periodically, once a second, the receiver is turned on, and the receiver is listening on very specific channels for those up to 16 LoRaWAN endpoints. The relay works a little bit different than an endpoint. So it identifies itself to the network as being a relay, and then the network knows a set number of frequencies that relay will be communicating on. It's aware of that once every second timer interval coming around. And this is what enables the device to minimize its transmission. Typically in a mesh, every endpoint is forwarding traffic at almost random times, which means that the transmitters, the receivers always have to be on. It drains the batteries really quickly. So the technical committee spent a lot of time and effort to make sure that this was implemented in a way in which you get that extended range, you get the long battery life, but you also get low cost and low complexity. So this is a fully released spec. There are a number of companies now who have developed relays, and those relays are now starting to be deployed in LoRaWAN networks. So one of the reasons why companies like Facebook and other back in the day startups were successful was because they were able to encode data and send it to a known IP address, their servers, in a format that their servers could understand that data. And it creates a very level playing field. It democratizes the internet because any endpoint can be programmed to connect to any other endpoint or server on the internet. But it's deeper than that. An IP layer also makes sure that all of the data coming down is being packeted up into the size frames that that layer underneath is expecting to see. So in a world of LoRa, if you're on a spreading factor 12, which has a very small amount of payload and a lot of protection, you're going to need a lot more frames of data than maybe spreading factor 7, which has a higher amount of data and less protection. An IP layer takes care of all of that as well. So it takes care of concatenation, frame signaling, and making sure that all of those frames successfully get to the other end. This frees up a lot of complexity for developers. It enables developers to sit above that layer, to be able to send messages directly into the IP layer without having to take the responsibility of knowing what spreading factor, what the size frames are, and how to concatenate that message up. So this is all based on an IETF standard. So this is completely standards-based approach to doing IPv6 over a constrained radio interface like LoRaWAN. And it enables a lot of applications now to be developed and immediately used over LoRaWAN. So the example that was given this morning was DLMS, which is a standardized protocol for metering, which by using a standards-based IP approach and a standards-based LoRaWAN technology creates a complete stack of standardized technology that can be embraced by utility industries. So we also heard this morning about application payload codec. So when you don't have an IP network, which is the vast majority of LoRaWAN deployments, at some point in the network server, you need to be able to take that data, understand what the payload data from those sensors is, carve it up, maybe if it's a temp sensor, and there is at least 180 LoRaWAN temp sensors on the market, but each one of those sensors probably has a different way in which it encodes that temperature. Some in centigrade, some in Fahrenheit, some as an integer, some as a decimal number, some maybe as 3 or 4 bytes, maybe others 2 bytes of data. So even as something as simple as temperature is represented completely different by one vendor versus the next vendor. And one of the friction points in LoRa is that you need to know what sensor you're using, you need to know how to decode it so that you can package it up and then send it over an IP backhaul to a platform or a cloud service. So what we've done here in the LoRa Alliance is instead of trying to standardize how a temp sensor should do its decode, instead we've standardized the APIs to access a repo. And in those repos, there will be tens, hundreds, maybe thousands of decoders for every LoRaWAN sensor on the market. Actility and the Things Network, both here over in the marketplace, have been early adopters in creating those repos. So here at the LoRa Alliance, we've standardized an API that enables any network server to reach out to a repo, pull a file, and then typically in JSON, you'll have a complete decode of that sensor or actuator. So it's really a implement the decoder once, populate that decode file into all the different repos that are on the market, and then have a standardized API to get that. So once upon a time, there were 2 LoRa networks that wanted to share data with each other. As a customer moved from network 1 to network 2, they still wanted to be able to send that data back to the home network. And so a connection was made. Then there was a third network. Now, the first network needed to speak to the second network, but it needed to integrate to the third network, and the second to the third and to the first. And eventually there was a fourth, a fifth, a 10th, a 20th network. And this constant integration of the new network to every other network becomes unscalable. It becomes an interconnect of mesh that is super complex to manage. And so having a star and spoke model where every network is connected into the hub, so as the next network connects in, there's only one connection that has to be made rather than n-1 connections. And so that's the concept between the roaming networks and the need to have to interconnect each other network, opening up the firewalls, configuring the data path, doing the authentication of each of those networks, really collapsing down that complexity. So the hub acts like a broker and is able to connect any new network into that hub. So it simplifies setting up and managing global roaming across a vast number of LoRaWAN public-private hybrid networks. So most of the LoRaWAN spec up until now has been dedicated around a model of devices to gateways, and then the gateways send that data onto a data platform or a network server software platform in the cloud. So D2D refers to device-to-device communication. So that could be something like a clicker that I'm holding right now, or something like a garage opening fob, where there's a connection between this device and another device. Instead of going through a gateway, they are connecting together. And that enables a faster latency for remote control operations. And it sets up a direct link between the devices that does not require the complexities of gateway scheduling and the network infrastructure associated with that scheduling. It also reduces on-air time restrictions, because if a device has to keep talking to a gateway, communicating with a gateway, then that gateway can hit its duty cycle limitations. By doing direct-to-direct device-to-device communication, that duty cycle can be load balanced more efficiently. So the spec is a baseline today to get moving, and it's a technical recommendation so that we, the ecosystem, don't have to just figure out how to reinvent this ourselves. Instead, we have clear guidelines. So in this market in Japan, it's a regulatory requirement to do listen before talk. So as the name would suggest, if I want to talk to you guys, the devices, I wait until you guys are all quiet, and then I communicate what I would like to say. So I make sure that I do not trample over your conversation, interrupt your conversation. I make sure there's always a quiet time for my message to be successfully transmitted. And CSA builds upon that. It's not a regulatory requirement, but it builds on listen before talk to be able to schedule a more efficient communication when other LoRaWAN devices are not active. So it's not listening for no activity on the channel. CSMA is listening for other LoRaWAN transmissions. As we know, LoRaWAN can far excel most other RF technologies, typically down to 17, 18 dB below the noise floor. So we're not so bothered about other FSK communication happening on the channel. Instead, CSMA is making sure that no other LoRaWAN communication is happening, and that's when the message is communicated. So that's a key difference with other radio channels, radio technologies, that may be using the channel at the same time. But of course, the excellent noise immunity and coexistence of LoRa enables us to use that channel without affecting those other radios and those other radios affecting our performance. So the advantage is a reduction in packet loss and thereby greater capacity on the network and thereby longer battery life for the endpoints. So not a regulatory requirement, but a way in order to extend capacity and battery life of devices. So this is a bit of a candy slide, a bit tricky perhaps to get your head around. But what this slide is showing is that LoRaWAN continues to expand. As Donna highlighted in the keynote earlier on today, what started off as a radio link specification in the first couple of years of the LoRaWAN spec back in 2015 grew. It grew to be more than just a transport spec. It started to focus on regulatory approvals and how to set up channel plans in different countries. It enabled back-end roaming and integration of other networks. And then it built on that by bringing in operational features such as firmware updates and multicasting. And LoRaWAN continues to expand its reach by now integrating into different types of protocols like BACnet that might be used in a building management system, Modbus that may be used in an industrial market, DLMS, which we have technical link layer specifications for metering. So LoRaWAN specs continue to remove those friction points, and they continue to expand into different vertical markets and applications. So that's kind of what that slide's trying to say there. So the work hasn't stopped. There's more work going on at the LoRa Alliance than there ever was. And there's a number of different task forces and working groups. So we're looking at core specs like layer 2, back-end, regional parameters, security. Looking at different vertical markets like utilities, where roaming, updates, IPv6, device profile updates, and even using LoRaWAN over satellites now. Enhancements with CSMA to be able to reduce collisions, improve network density and battery life, and collaboration with other industry working groups and technical alliances around the world. So these groups are open to all of you. Any of you whose companies are members of the LoRa Alliance, even if you're not a sponsor and a contributor. These groups are open to all of you to participate in. We welcome the domain experience from different vertical markets and regions, and we welcome your input into building the new specs that are coming out for the increased coverage of LoRaWAN. Any questions? I'm happy to take a few of them at the back of the auditorium here. And if I can't answer the questions, I can definitely put you in touch with those who have written some of these specs. Thank you very much.